Alright, and welcome. My name is Nate Nestler. I am a developer, a programmer for the 3D game and film industry. I'm also an artist and a network engineer. I'm what's called a technical artist or a technical director in the game film industry. So today we're going to have a look at doing some 3D graphics programming with in mind of real-time aspects, but this stuff can also be done for post-processing graphics, meaning that these are graphics that take a long time to compute and then to be played back as video later on. So these techniques can be used in either or method. And particularly in this case here, this is an example of a post-processing software. This is Blender. This is open source, meaning that the source code is available freely to be read and used. But this allows you to actually navigate the scene, and the scene is being done with OpenGL. And there's a couple different languages out there. There's OpenGL, there's DirectX, and there's some different shading languages. HLSL is for DirectX, and that's the shading language that defines the look of the model here. Right now it's faceted with just a very basic shader applied to it, but we can actually change that around easily. And then for OpenGL, it's going to be GLSL. And then NVIDIA's put out another method called CG, which lets you code in one language and essentially kick it out for GLSL and HLSL. So it's very nice. And this way you can target multiple platforms like Sony's PlayStation 3 or Xbox 360, et cetera, or PC. It doesn't matter. It's such a great thing with the NVIDIA CG shading language that Sony decided to make that the shading language requirement for PlayStation 3. So that's why PlayStation 3 is done with the CG shading platform. As we get more into CG shading language, we'll be talking about why it has so many benefits to it and why it's such a great thing. But for now, let's have a look at the actual object in this 3D environment. And yes, you will be programming stuff like this. You will literally be creating 3D. Let's get first of all, you would not program a beautiful 3D model sculpted and all this stuff. That is to be done by artists, and then you are going to import that model from the artist and then do your coding on the model. Now, you might write the importer, or you might write the shading effects, or you might write the animation system, but you're not going to actually write the artistic nature of the animation. That's going to be done by an artist in a program like this, and then you're going to need to import that animation. Some of the popular programs out there for doing that 3D stuff: Blender, Maya, XSI, Houdini, ZBrush for 3D modeling, sculpting, texture painting. It's very nice. There's Mudbox. There's 3D Studio Max. There's a whole Cinema 4D, etc., etc., etc. There's a whole list of programs out there, and each one has its benefits and strengths. They're very nice, and so there are certain formats that go across the board that I'll work with, and then be like the OBJ format, for instance, or the Collada format, are the two big ones, and FBX for Motion Builder format, which is an animation program. These three formats are the main ones which you can actually send this art. Like, for instance, if I want to send this monkey to another program like Maya, I could use one of those formats. OBJ is probably the most reliable of them all, just because of standardization that occurred from ZBrush back in when it first became big around ZBrush 2.0. But all this aside, we do want the models, we'll go into this later on, to be triangulated, to be, if we're doing in-game, and the reason why is it computes faster, and we don't have to worry about non-coplanar surfaces, meaning that, okay, say if you have a model like this, and I were to take one of these points, I could literally grab them, and then twist it in a way that wouldn't be so good. Alright, so you see that where the model is starting to kind of break up here around that face, and I can twist this face in such a manner that it doesn't really even act flat anymore. Like, I could even pass it back through itself like this, and then that's nasty. That's not going to render properly. It's because it's messed up. But if this is triangulated, there would only be 3 points, and so no matter which direction you align, 3 points is always going to be flat. So that is why you want to be triangulated for one. That's one reason alone. for wanting it triangulated when having it in game, and it should always be triangulated. Now artists typically will not make it triangulated, and you'll have to make it triangulated. We'll get into all this stuff later on, but it certainly helps if you have, when you're importing the models with one of these formats, to have it where it automatically triangulates for the artist, because typically you're going to get all kinds of crazy stuff like triangles, quads, and ingons, where quad is a 4-sided polygon here. These are called polygons, by the way. This is the primary method in which games are done. You're not going to see NURBS in the games, just are non-rational B-splines. And that's basically a bunch of calculus 3 based curvature algorithms, and it's unwieldy, it's difficult to manipulate from a programming standpoint for artist tools. They haven't really ever really taken off. Some years ago, about 5 years ago, they were popular for doing organic surfaces, but pretty much it's gone polygon all the way, but they were never real popular for games. It's pretty much been polygons the whole time for games. But OpenGL will support both. But regardless, you're going to want to go with polygons. So our focus is going to be towards polygons, because this is realistic of what you're going to expect to see in games. So here we got a couple different things. Now we have world space. This is world space. See, this means that we have it's an arbitrary definition of a space, a point in space, more or less. In this case, we're doing 0, 0, 0, and we placed it here, right in the middle of this. You can see it right there with the red and the X cross. And you'll notice, and this is standard, Z is blue here, green is Y, and an X is red. And this defines the world coordinate space in 3 dimensions. So when you're creating a world space, you're always going to have it about some imaginary point here, and then all the units are based on, you can say inches, feet, or whatever. It's really all arbitrary. Really, it comes down to relational. This units here is feet suddenly. So this number of feet and this units according to the relation of this size for this object and this number of feet. And this number of units. So you could really actually convert the units back and forth all day long on this stuff, and it's all really just based on mathematics. So it's just really just 1 unit here, 2 unit here, 3 unit here, and then you can say it's feet, inches, whatever you want, pretty much, and then that just determines for scale, for human use for like buildings or whatever it is going to be. For a game. I mean, as far as the game is concerned, they don't need feet or anything of that nature. It's usually just units. Like it's just 2 units over here, 3 units over there. Who cares? You don't need inches and feet for the most part. So for that reason alone, you have to have a point of reference. Now, in order to make life easier for transformations, for doing these vector transformations with the matrices, and we'll get into matrix math and the vector math. Check that out in the matrix math and vector math series here. So we're going to have a whole math series that's going to cover this stuff, including calculus 1, calculus 2, calculus 3 type calculations that are involved and are required pretty much for doing some of this 3D programming, because it's pretty much what it takes to do some of this stuff. But basically doing the mathematics here, you can sit there and go between the different stages in handling the way the view comes out, and it's the way the hardware calculates it. So here we have our world space, and so this makes this object positioned in accordance to, say, this light over here or this camera here. And basically I could even move this object, and now this object is now moved up however many units up. If I want, I can check that out. It's been moved up 2.563 units up in accordance to the world position, and then the light's different position over here at, X at 4.076, and then Y at 1.005, and Z at 5.904, etc., etc. You know what I mean? So they're all being relative to this center point position for the world space coordinates. So that's basically world space coordinates, how that works. Now, the important aspect here, I'm just going to move this back to the center because I like it there. The important aspect to realize is, in order to make life easier, say I just want to move this model up here and then say rotate it or something like that. Well, that's all fine and dandy, and I can easily manipulate that in this program that's been coded out to do this, but from a programming standpoint, you want this to be as easy as possible. So we do have a method to make this easier. We're using matrix multiplication, where we multiply the matrix through all the vertices, or points, depending on how you want to refer to it. Typically referred to as points, or vertices, I mean, in OpenGL. But you'll see it referred to in both ways. Now you see every single one of these points or vertices make up this model, and you can have a command in OpenGL literally create this quad. And it's create quads actually. GL quads will let you create a quad, and you can create a quad strip, so you could do a whole list of these polygons going together to form up this model here, etc., etc., etc. And here you can see a triangle, in addition to the quad next to it. And so we got a mix of the two. And all these points, based on using this matrix transformation, this is called object space here. So all these points are relative to the object space. Now the object has its own center, and it's a centroid point, as it's called in mathematics and calculus 3. But basically all this is a fancy term for saying it's the center of the object. If you were to take, say, a plate and were to balance it on your finger, that would be the center point where it balanced. That would be the centroid. Well, you can define your own center point or whatnot, but it's basically the bounding box, if you will. If you can imagine a 3D box around this model that would encompass the full size of this model, that would be your bounding box. This is a quick example. Let's go ahead and add a box here, and maybe I can make that a little more clear. Okay, so here we go. We have our quote-unquote bounding box for the most part here. And if I were to switch this over into wireframe real quick, if I were to pull that out a bit more, okay, so that would be your bounding box. It fully encompasses this model. And here's for an orthographic view versus a perspective view. That's something else that matters. And this goes into screen space manipulation. We'll get into that a little bit more here. But first, let's continue to talk about our object space here. Yes, that's still selected. That's why. Okay, so all these points are in relation to each other based upon this center point and object space for this model. And the model is moved according to that object space in world space. So if I were to move the bounding box, more or less, or the centroid point of this model, all these vertices relate to that centroid point, if you will. And then basically the rest of the model is going to move along with it. So by moving that centroid point, which all these vertices are based on, it moves the whole model. Now the way that works is that we actually have a matrix that we multiply, and this is where I get that term for the movie, but we actually have matrices here that we use for transforming and manipulating these models. Basically what we have is a transform matrix, a rotation matrix, and a scale matrix. And depending on, well, basically, say I want to move it first, then rotate it, and then scale it, then I'm going to actually multiply the matrix times the translation last, and I'm going to do the rotation second, I'm going to do the scale first. So you do it in reverse order of the way you actually want it to be applied and to be done. And thereby, if we multiply all these matrices together, then we can do a single transformation of these vertices all in one go. That sounds a little crazy. Alright, so that's complicated and doesn't make a whole lot of sense. Don't worry, I'm going to make it make sense here in just a second. So basically what I said, from a technical standpoint, let's break it down to where it's simple. Okay, so say we have all these vertices, right? I want to transform it first. Okay, so technically I could sit there and just take a transform matrix and multiply it times every one of these vertices and move it upward. Okay, like that. And then I could sit there and do a whole nother operation and say I want to rotate it now. Then I could sit there and take a transform rotation matrix here and multiply it times this in order to make it rotate. I could even make it rotate separately on X and Y and Z. Well, now remember, every time we're multiplying this matrix for it, we're going to multiply that times every single vertex and reposition every single vertex in this model interactively. I mean, like on the fly. So we just, how many points are in this model? If it's like, I don't know, several hundred. Say there's 1,000 points in this model, right? That means we just did this operation, what, 3,000 times? Maybe 4,000 times. So we did it for the pull it up in Z, and then we rotated about X, Y, and Z. So Z for Z is just because it makes it easier to hear it. Sometimes Z and C sounds alike. That just means we just did 4,000 computations right there just to rotate and position it. Now say we want to scale it. Oh boy, now we got to scale it with a scale matrix. Okay, so now we scaled it, right? Well, there's another one. That's 5,000 operations. Okay. So what I just said earlier is we could actually multiply these matrices together to get one matrix that encompasses the scale, transform, and rotation all together, and thereby only having to multiply that combined matrix times all these points to get it to what? Translate, rotate, and scale all at once, basically. And that's why we have to do it in reverse order when we multiply them through if we want to get it going in a forward order. Meaning that if we want to translate it first, we have to multiply it last when we're doing the multiplying. Once we get our combined matrix that has the translation, rotation, and scale, then we can actually multiply that times each vertice and position each vertice. Now we'll look at this later on and how to do this from a mathematical standpoint, and you'll have to go through a whole series of mathematics videos and stuff for explaining all this stuff in detail, but that's essentially what's going on, and it makes it much, much faster. I mean, which would you rather have? Literally what this does, as just an example here, so say we had translation, rotation, and scale, and we want to do it in that order. So we're going to multiply scale first, rotation, then translation, matrices together to make a combined matrix. So that's what? 3 operations, right? Because we're multiplying each one of those together. And then we have that combined matrix, and we multiply it times each vertice. So what are we talking about here? 1,003 operations versus 5,000 operations. So of course 1,003 operations is going to compute much faster than 5,000 operations. This is where you get into obviously this is much faster. It's about 5 times faster, over the other method. And here you just managed to do something as simple as that, speed up your game engine 5 times faster. So the name of the game when it comes to doing 3D game programming is fast, fast, fast. How can we optimize this? How can we cut out processes we don't need to do? Let's not stupidly just loop through something to make it do something we want it to do. We have to do it in a smart manner. This course really focuses on some of the 3D graphics programming, but it's going to involve C and C++, as we go through this. So you do need to be versed in C and C++. If you are not, you can go through our C++ course set, taking all the way up from beginning C++ up through advanced C++. So please check that out if it's going to be something you don't know already. Okay, so let's reposition that back to my center point, because now remember, I was moving these points in object space. If I were to, okay, I'll just prove this real quick. If I were to pull this up, now it's according to the centroid point for this model here, and I've moved these points away from that centroid. So now this is the balance point for this model. Now I'm back in world space, okay? So, I'll go ahead and move this model according to world space, but it's based off of the center point. I'll even prove it by rotating this. See, it rotates about that point. And then that's the object's centroid point, more or less, or its balance point, if you will. If I go back in here and move this back, and now come back into my world space and move about this model, you can see a difference in how it rotates and moves about that point. So your point of reference for which you manipulate a model for its matrices really matters a lot, and that can really make a big difference for a change of how it works. Why does this matter? Okay, well, because the computer is going to do a certain set of operations where you're computing it, whether it's in DirectX or OpenGL, you're going to go through a certain set of steps to process the viewport on the graphics cards in order to make it look good. So, what are we looking at here? Well, we looked at object space, right? And then we need to move into world space from object space. So we do a modeling transform, okay? And what that just means is we multiply those matrices I've been talking about. That's basically what that means. And we can work in homogeneous coordinate system, or we can work in non-homogeneous coordinates. Let's talk about that real quick. So dealing with our vectors here, we have an example of how they can move between homogeneous and non-homogeneous coordinate system. So here is our X, Y, and Z. And then we add a W for homogeneous coordinates. As you expect, of course, X, just like you learned back in geometry in high school and middle school and all that fun stuff. You have your X moves along your normal quadratic coordinate system here, where you have X goes crosswise, Y takes you up and down, and then Z goes in and out for depth for Z. If you have a third coordinate system, which you're not used to seeing in high school, because you'd have to reach that at Calculus 3. But essentially, that lets you move in and out of depth, and that's simple enough, really. Just think of depth as Z for the most part. Now you'll notice this other program here, Blender, is using Z as up and Y as depth. That's usually used for the purpose of physics calculations, and some people will prefer to use that method where Z is up and Y is in the depth versus X is crosswise. X is always crosswise for the most part. And so you get two different standards here. You got where Z is up in some programs like Blender and Max, and then in like Maya, XSI, Houdini, etc., Y is up instead. And so if you take this in consideration, say you do your game as Z up, but you need to import models from Max, then that means you're going to have to convert your coordinate system from Max into your coordinate system for your game engine. So that matters. But for our purposes, we're going to be looking at X is to the side, Y is up, and Z is depth, because that's just more straightforward for most people and it's easier to follow. But physics people will literally switch it around on the coordinate system. Sometimes it makes some of the calculations easier, and you'll encounter some of that in calculus too, for making some of the calculations easier if you manipulate the coordinate system. So just because of the way the mathematics work out, sometimes it's easier to calculate about a certain axis easier than it is to do another axis. But since it is arbitrary, you can really do that. It's no problem mathematically. But for most purposes, you probably do want to stick to the X, Y, Z, where X is crosswise, Y is up, and Z makes move back and forth in the depth. If you do choose to go the other method, please choose be Z up and then Y in the depth and X across. Those are the only two really different setups for the most part. As far as that goes, there's really no one does X's up. So if you did that, you'd be non-standard with basically every program out in the industry I've seen, period. And I've seen just about every program at this point in time. I've been around the industry since, since 3D Studio Release 3 before Max was, so almost at the very beginning of the industry when it started. It started at a very early age in this industry. But basically, with this setup here, this allows us to have X, Y, and Z position. What's W? Well, W is a scalar, more or less. W lets you resize your X, Y, and Z across the board. So why does that matter here? Because say I wanted to do 1/10 of the magnitude of this vector, all I have to do is put in 0.1, 0.1, 0.1, and sorry, 10, 10, 10, 1 10, 10. If I ever do 10, 10, 10 across here, and then I'd make this 1/10, 1/10, 1/10. And this is how you go from homogeneous to non-homogeneous coordinate system here with this equation. And it shows how to do it. Most of the time, we're going to be using 1 for W, because if you notice, if you do 1 here, you just get what? X, Y, Z. And so that's literally how you can go between homogeneous and non-homogeneous coordinates. It's really fancy terms to say non-homogeneous is just X, Y, Z, and homogeneous is just X, Y, Z, W. But I'll keep bringing this up over and over again to pound it into your head, these different terms, so that when you hear it or read it somewhere, it's not, oh my gosh, what on earth are they talking about? I can't remember. I know I read it, I know I saw it, but I can't remember it. So let's I'll keep going over and over some of that stuff to help get it in your head. Okay, so what have we talked about so far? We talked about going between a couple things here. We talked about going between object space, modeling space, and world space. Alright, in the next video we'll talk about going further with this, and then that will be going into further in the pipeline, because I talked about some of these other things, get a little bit of a precursor to perspective and orthographic, and we'll talk about how to actually manipulate the screen coordinates and how we're going to adjust these vertices in order to be set up for screen perspective distortion and all this stuff. That's very important, so that things get bigger as they get closer to the camera and they get smaller as they get away from the camera. We'll get into that in just a bit. But this is the first setup here. As we move into getting to where we're set up to program some of these cool shader effects, and it's really neat and it's really awesome, and we'll have a look at that in just a bit. So let's have a look at the next video.